This portion of the lesson focuses on transformations from the parent function. So we're going to be looking at transformations of quadratic functions. If you remember transformations from just looking at geometric shapes, what we're really looking at is how on the graph a particular shape, right now a quadratic function, can move around. We're looking at if the graph will slide, which we call translate, left or right, or up or down, if it will shrink or grow in any way, which is like a dilation, and then eventually you might look at it doing other things. But for right now, we're mostly looking at if it kind of slides around a little bit. So before we get into some examples, let's take a look at some fill-in-the-blank notes. The most simplistic quadratic equation is y equals x squared. So this is actually called the parent function. You're going to learn a lot more about parent functions a little later down the road, but parent functions are what would the graph of this type of function look like before anything happened to it. So that is the parent function for a quadratic equation. If we go back to thinking about lines, technically the parent function of a line is just that perfect line that goes to the origin with a positive slope, which is y equals x. So that's the parent function of a line. The parent function of a quadratic equation is y equals x squared. Okay, so this is known as the parent function. Okay, a transformation is a blank to the blank or blank of a figure. So a transformation is a change to the size or position of a figure. Change to the size or position of a figure. So we're going to look at how these parabolas are changed either by stretching or growing. We call them stretches or compressions, and then the position if it slides around at all. Before we do any of the examples on the sheets, I just kind of want to look at some Desmos examples with you. So this is what the parent function looks like. Y equals x squared is a parabola that is symmetrical about the y-axis. Its vertex starts at 0, 0. Now with vertex form, I'm going to plug in some different equations in vertex form and see how our graph moves around. So if I pose to you a vertex form y equals x minus 3 squared plus 2. Okay, so this red one is our original and this blue one is our new one. So now that we have an idea about vertex form, I know that this 3 inside should represent the new x-coordinate of my vertex, and this 2 outside should represent the new y-coordinate of my vertex. So we know that because the original one started at 0, 0, and now this is telling me my vertex, but it's really telling me how the vertex is going to shift from its original position. So our vertex went over to the right 3 and up 2, and if we had pulled out the vertex from this form, we would have said that it's the point positive 3, 2, and that's because we know there's a minus in the formula. So vertex form is another way to actually see the transformations of the equation. Now this actually works with absolute value functions, with all kinds of functions. And there's this little saying that I like to say that helps me remember what is being affected. If something is inside of the parentheses or inside of the function, it is affecting the x-coordinates, just like this 3 is affecting the x-coordinates. If there's a value outside of the parentheses, sometimes we say outside of the function, but if it's outside of the parentheses, it is affecting the y-coordinates, much like how this plus 2 is affecting its shift up on y. So the number inside the parentheses can tell us how much it shifted left or right, because those are on the x-axis. The number on the outside can tell us how much it shifted up or down, because that affects the y-axis. So taking a look at our first example, they want us to graph each function and describe how it compares to the parent function shown on the graph. So truly, we don't even really need to do all of this. I really just talked to you about it through Desmos, so I'm not going to make you fill in this table. Let's kind of look at this function and see if we can pull out the new vertex and talk about what changes we see. So the graph that's on the coordinate plane right now is the parent function. The vertex is at 0, 0, and it is in standard traditional quadratic form. So from the equation they're giving us, if we pulled out the new vertex, we would know that the new vertex, remembering that 2 originally had a minus in front of it, is -2, and since there's no plus or minus anything outside, the y-coordinate remains unchanged. If this is our new vertex, so it's at -2, 0, it's going to be shifted over a bit. So I can fill this in, and I probably will in a second, but I just want you to see that without even plotting the points, we can actually see how the graph's going to change so far. Mostly because I don't have a number out front making any differences. Right now, all that's changed is the vertex. So I can see that this shifted back left 2, and it did not go up or down. So it shifted to the left 2. So we are going to fill in the points just to remind ourselves how to do that. So we know our vertex is at the point -2, 0. We know that in our transformed function that the axis of symmetry should be going through x equals -2. So we know we need to pick some points on either side. So I'm going to pick the points -3 and -4 above it. And I'm going to pick the points -1 and 0 below it. And if I plug those in, I've got -4 plus 2. So if I plug in this one, I've got -4 plus 2 squared, which comes out to give me a -2 squared, which is a +4. If I plug in -3 plus 2 squared, that comes out to give me -1 squared, which is a +1. We already know the vertex. So if we plug in -1 plus 2 squared, that's going to give me a 1, +1, and 1 squared is 1. And then 0 plus 2 squared is just 2 squared, which is 4. So we need to plot our new ordered pairs. We've got -4, 4, so 1, 2, 3, 4. -3, 1. Then -1, 1, and 0, 4. So another way, well, let me go ahead and draw this. Another way we actually could have done that, instead of necessarily plugging it all in, we could have chosen some points. So say I wanted to pick some good, clean, ordered pairs that I saw on my original graph, and just like my vertex shifted left 2, all the other points on the graph are going to shift left 2. So if I find some good, clean points, all I got to do is take that, go back 2, put it here. Take that, go back to, put it here. Take this one, go back to, it ends up here, and this one goes back to and ends up here, and I could have plotted them. So you could have done it by plugging it all in, getting some points, or you could have just shifted all the good, clean, ordered pairs that you see back to. Again, we knew that from looking at the vertex form of the equation, pulling out the new vertex, and remembering that it originally starts at 0, 0. So for the actual description of the transformation, the parent function translated, that means to slide, 2 units left. Sometimes they'll call that a horizontal shift because it is moving on the horizontal axis, so it's moving over 2 to the left. All right, number 8, taking a look at the transformations. So originally I said something about this being standard form earlier, and I think I misspoke because it looks like it because there's no parentheses. So the reason why there's no parentheses is because there's no changes happening on the inside of the function. So this could truly be seen as x plus 0 squared with the plus 5 outside. That's how we could also look at this. Because there's nothing being added or subtracted inside, it's just x squared. So when I look at it like this, the point of the vertex is going to remain 0, and the point of the y-coordinate of the vertex is now going to be 5. So from this parent function, this is going to not shift any left or right any, but our vertex is going to move up 5. So 1, 2, 3, 4, 5. So that's where our new vertex is going to be formed. And this time, instead of picking all the values and doing all that, we're going to try the alternate method of just finding some clean points and shifting those up. So if I want to do this way first, I would be looking at my ordered pairs and seeing if I find any good clean points where it looks like it's going through the crosshairs. So I see a couple of them that look pretty close. So all of these, which I think we're going to run out of graph, but all of these would need to shift up 5. So this particular point would go up 1, 2, 3, 4, 5. This one would go up 1, 2, 3, 4, 5. And if I had enough graph, 1, 2, 3, 4, it would really be like up here. So this is where my transformed quadratic function would be. It shifted up 5 units. Now this time I'm not going to make you fill that in. Really, you could actually just go back and read the ordered pairs if you wanted to. I could say this is at -2, and that looks like that would be 9. This one is at -1, 6. Our vertex we know is at 0, 5. This would be at 1, 6. And then this one would be at 2, 9. So honestly, it came out to be easier anyway. We could fill in the ordered pairs. So the actual transformation is that it translated, so slid, translated 5 units up. So it was a vertical translation that time. So this time it went up on the vertical axis, on the y-axis. Taking a look at this one, we start with 0, 0, and you have some changes on both the inside and the outside. So we see if we were to pull out our new vertex, keeping in mind there was originally a minus, this would be the vertex of -1, -6. So I know if it started at 0, 0, and it went back 1 and down 6, the whole function is going to do that. Any clean ordered pairs I find are going to do that. So if I use these 2 ordered pairs, and it looks like these are meant to be 2 clean ordered pairs, if I use those to move them, this particular point would need to go back 1 and down 6. So back 1, down 1, 2, 3, 4, 5, 6. This one goes back 1, down 6. This one goes back 1, down 6. So 1, 2, 3, 4, 5. And this one goes back 1, down 6. So our new parabola is going to be down here. And if we wanted to write our new ordered pairs, we could. So our new ordered pairs are -4, say, hold on, 1, 2, 3, sorry, -3, -2. Then we've got one here at -2, 1, 2, 3, 4, 5, -5. Then we've got -1, -6 was our vertex. Then we've got our other ordered pairs here and here. So this one is at 0, -5. And then this one's at 1, -2. Okay, so a couple things happened there. The original one translated 1 unit left and 6 units down. So there was both a vertical and a horizontal translation. So it shifted back and then shifted down. So I could have also taken all of these ordered pairs. If I had a table of the original ordered pairs, I could have subtracted 1 from all the x values and subtracted 6 from all the y values, and it would have given me these ordered pairs. So our description of the transformation is it translated, or a horizontal translation, it translated to, I'm all over the place, translated 1 unit left and 6 units down. So once again, if it goes left or right, that's called a horizontal translation or horizontal shift. If it goes up or down, it's called a vertical shift. All right, so we're moving on to number 10. I know, unfortunately, this seems like a really long lesson, but honestly, if I don't do almost all of these examples with you, you just won't have good examples of them. So we're just going to try and power through and get them all in. All right, on number 10, looking at what we can already see from what we know the vertex changed. There was a shift on X and there's a shift on Y based upon where the new vertex is. We know our vertex is now at a positive 4, because remember the minus is in the form, and a positive 1. So this vertex is going to be over at 1, 2, 3, 4, and up 1. So we can put that in the middle of our table for when we graph here in just a second. But this time there's something a little bit new happening. There's a negative out front. So we're going to actually see how that changes the original graph. So we're going to do what we were doing for a while. We know that the axis of symmetry is going to go through this x equals 4 because it always matches the x value from the vertex. So when we're choosing some points to plug into this equation, we're going to pick a couple to the left and a couple to the right. So I'm going to use the x values of, let's see, 2 and 3 above it, and then 5 and 6 on the right side of it. We're going to plug these into the original equation to see if we can get some values to see what this new graph is going to look like. So plugging it in, I'm using substitution. I'm going to substitute in that 2. So we've got negative. We would have negative 2 minus 4 squared plus 1. Inside parentheses first, we'd have 2 minus 4 is a negative 2. Minus outside of it, it gets squared and 1 added to it. Negative 2 squared is a positive 4, but there's a negative out front. So negative 4 plus 1 is going to leave us with a negative 3. I'm going to plug in the next value again to just remind you how we're doing this. We've got negative 3 minus 4 squared plus 1. Inside the parentheses, we're going to have a negative 1 squared, which is a positive 1. But there's a negative out front, so it goes back to negative 1 plus 1 is 0. So if we continue this, when we plug in 5, we should get 0, and when we plug in 6, we should get negative 3, and that's only because I went at even intervals based upon the axis of symmetry. I'm trying to expedite this process here. So to draw your new ordered pairs, we've got 2, negative 3, 3, 0, 1, 2, 3, 0, and then 4, 1 is our vertex, 5, 0, and 6, negative 3. So this is our final transformed graph. So we already knew that the vertex was going to shift a little bit, but now it's facing down. If you recall in our first lesson, we said if the number out front, if A, the leading coefficient in standard form is negative, it's going to make the graph be facing down. So that's actually what's happening here, because even though this is not standard form, in vertex form, it is y equals a times x minus h squared plus k. Whenever this a value out front is negative, just like in standard form, whenever it's negative, it's going to be facing down. So that's what happened here. In the original parabola, it's facing up, in the original parent function. So there are 3 different transformations happening here. This thing moved over to the right, it moved up, and it flipped. So transformations are that there was a reflection. Now the big picture here though is, did it flip over the x-axis or the y-axis? So this was facing up, it is now facing down, so it actually flipped over the x-axis. If it had been facing over the other way, it would have been considered being flipped through the y-axis. So this is flipped down. Now you remember me kind of mentioning if things are happening on the outside of the parentheses, they're affecting the y coordinates. Well, this outside negative means that the y coordinates are going to change their signs. So all of these positive y coordinates on the original one are now changing their signs. So there are a couple things that happen, but that's particularly what the negative's making happen. So since it flipped over the x-axis, we're going to say that there was a reflection over the x-axis, and it does matter that you know which one it flipped over. We're going to start using more descriptive words here. There was a horizontal shift, to be very accurate, horizontal shift, and it went 4 units right, so 4 units to the right, and then there was a vertical shift, 1 unit up. So it flipped down, it went over to the right 4, and it went up 1. Let's take a look at this next one. So 3x squared minus 7. Originally it's at 0, 0. Even though I don't have a parentheses, I know that I can really visualize this as 3 times x plus 0 squared minus 7. So the reason why there's not a parentheses is because nothing's being added or subtracted inside. So I know that just looking at the new vertex, x didn't make any changes. Technically it would be minus 0, doesn't really matter. There were no changes to the x coordinate, so it's going to continue to stay 0. The new y coordinate is negative 7. So in addition to our new vertex, though, we do see something different happening here. So we're going to figure out what that 3 outside does. So let's just focus on what we know how to do so far. So I know that 0, negative 7 is going to be my new vertex. So it's going to go down to negative 7, and that's where the new vertex is. In order to graph it, I'm going to go ahead and put that as the middle point. I know that the axis of symmetry is going to continue to be the y axis here. It's going to be the equation x equals 0 would be the line of symmetry here. Now I need to pick some points to the left and to the right of that vertex. So I'm going to go down to, so I've got negative 2, negative 1. Then I'm going to go right to, and a positive 1, positive 2. When I plug these values into the original equation, I'm going to erase all of this. When I plug these values in to get our new y coordinates, we've got, for negative 2, we've got 3 times negative 2 squared minus 7. Follow order of operations. Negative 2 squared is a positive 4. 3 times 4 is 12, and 12 minus 7 is 5. Then I've got 3 times negative 1 squared minus 7. Negative 1 squared is a positive 3. I'm sorry, negative 1 squared is a positive 1, and 1 times 3 is 3. 3 minus 7 is negative 4. Because we chose our values exactly based upon the axis of symmetry, they should match. So I've got 3 times 1 squared minus 7, which comes out to be 3 minus 7 again, which is negative 4. Then 3 times 2 squared minus 7, which comes out to be 12 minus 7 again, which is 5. So it's like a mirror image. So plotting these points, we've got negative 2, 5, so 1, 2, 3, 4, 5. Negative 1, 4. Then we've got 0, 7. Oh, sorry. I was wondering what I was doing. We've got negative 2, 5. 1, 2, 3, 4, 5. Then we've got negative 1, negative 4. 1, 2, 3, 4. Then we've got 0, 7. Then we've got 1, negative 4. And we've got 2, 5. So this thing is like really skinny. Do our best to make it look curved. Come back up, put your arrows on the ends. So if the black one is the original one and the blue one is our new one, we do know that the vertex shifted down 7. So at the very least, we know that there was a vertical shift 7 units down. So we can say that vertical shift 7 units down. But something else also happened. It got a lot skinnier. That 3 is a number that is outside of the parentheses. That 3 is affecting the y coordinates. All of the y coordinates are actually being multiplied by 3. They are changing by a factor of 3. They are increasing. So if I am thinking about this in terms of vertically, because this is affecting the y-axis technically, it looks like the original graph got skinnier. If that happens, if this a value, if this number out front is a whole number, or really even a fraction, but if it's a number greater than 1, it is going to cause the graph to get skinnier. We call that a vertical stretch. It looks like someone is taking the graph and stretching it. So it's gotten skinnier. And that happens when this number out front is a number greater than 1. Now, it could be a negative number, so technically it could also be less than -1, but the negative does something different. The negative is what makes it flip. I'm specifically just talking about the number out front. If it is a number greater than 1, then it is going to make it into a stretch. So number 12, there's a whole lot going on here. We've got negatives, we've got fractions, we've got something inside, we've got something outside. So our graph is going to look significantly different from the parent function. Let's take out what we know so far. We do know our vertex is going to move around a bit. It's now going to be at a +3, -2. So I know that that's going to move around a little bit. I'm going to use that to plug into the table. And we're going to choose 2 numbers below and 2 numbers above that. So we're going to do 1, 2, 3 is the vertex, 4, 5. I'm going to plug these values into this function and get some y values to see what on earth all happened to our graph. So when I plug in 1 to the original function, I'm going to have -1/2 times x minus 1 squared minus 2. Sorry, that's supposed to be 1 minus 3. I'm replacing the x with the 1. So 1 minus 3 is 2, and 2 squared is 4, and -1/2 times 4 is -2, then -2 minus 2 is -4. Now, I realize some of us can't do all that in our head. You are certainly welcome to plug this in the calculator exactly as it is and let it give you the answer. That is totally fine. So then we've got -1/2, 2 minus 3 squared minus 2. Inside the parentheses, 2 minus 3 is -1. -1 squared is a +1. +1 times 1/2 is going to be a -1/2. And -1/2 minus 2 is -5/2. You could have also written that as a -2.5. Now, because we specifically chose values both direction, equal distance from the axis of symmetry, from the vertex, I can now safely go ahead and fill in the rest and say that this is also going to be -5/2 and this is going to be -4. Remember, that could also be seen as -2.5. So let's plot these new points of our new transformed function. We've got 1, -4, 1, 2, 3, 4, 2, and then -2.5, so it's going to go down 2 and about 1/2. Then we've got 3, -2, 4, -5/2, and then 5, -4. So it's going to be facing down. Got to kind of round it out as best as you can. And comparing this one to the original, we do know that it flipped because the negative is going to make it flip. There's a reflection. We know that this 3 is telling us that since it's just a regular 3, that it went 3 units right, because that minus comes from the form. And this -2 tells us that it went 2 units down. The thing we didn't necessarily know yet is this 1/2 out front. So on the previous example, there was a number greater than 1 out front. the absolute value of it, basically. It was a number greater than 1. It caused the graph to look skinnier because it was a vertical stretch. Well, this time, this number is less than 1, and so our new graph actually looks a little bit fatter. It's a little wider. So if I'm thinking about it vertically, it looks like I took the graph and kind of squished it. It's kind of flattening out. That is called a vertical compression. So all the transformations would be that it was a reflection, and we know that since it flipped down, it was a reflection over the x-axis. There was a horizontal translation or shift, and that happened to be 3 units right. There was a vertical translation or shift. I'm going to use the word shift here, and that was 2 units down. And the new one is that there was a vertical compression by a factor of 1/2. Our other one was a vertical stretch by a factor of 3. I forgot to write that. Okay, so we've seen pretty much anything that could really happen with these. We now see the 4 major changes that can happen with a transform graph. So that's going to bring us to this wrap-up piece. We know that H is representing the horizontal shift. A positive H is actually shifting the graph to the left, and a negative H is actually shifting the graph to the right. And that's because the minus is already a part of the form, so it kind of does the opposite of what you think. K, basically the number being added or subtracted outside, is a vertical shift. Those are also translations. A positive K shifts the graph up, and a negative K shifts the graph down. If A is negative, so if the front number is negative, the function is going to reflect. So it is reflected across, specifically it's going to make it flip down, so it's going to reflect across the x-axis. If the number, the absolute value of the number out front, is a number greater than 1, it is going to be a vertical stretch. And if that number, the absolute value of it, is a number technically between 0 and 1, so some kind of fraction or decimal that's less than 1, it's going to make it a vertical compression. So those are all the things that could happen with transformations, and a lot of these things apply to many other types of functions as well. You've just got to be able to recognize them. Our final piece of this lesson is writing equations. So we're going to take this idea of what we learned about transformations and write the equations. So we're using the parent function y equals x squared, and we're going to look at the transformations and now plug those back into vertex form. So if it translated 2 units right, that means that the vertex went 2 units right. That's affecting the x-axis because you're moving to the right. So that change is going to happen on the inside of the function. So if it goes 2 units to the right, we're just plugging in a positive 2 to vertex form, because it's really like we're trying to basically fill in any boxes for any changes that are happening. So since this one was just 2 units to the right, I'm just going to put in a positive 2 in the box, but remember there was a minus in the formula. So this is actually the equation, y equals, in parentheses, x minus 2 squared, that would show a translation of 2 units right. Number 14, translation of 5 units up. So this time the only thing that's happening is something on the outside. So really I could put x minus 0, but I don't need to. I would just need to have y equals x squared and then a plus 5 on the outside. Translated 3 units left and 4 units down. So we're going to have a change on the inside and the outside. So y equals x minus is the original one. 3 units to the left, though, is like x minus negative 3, which is really going to make it x plus 3 squared. And 4 units down is going to give us a minus 4 outside. Final one here, translated 7 units right and 4 units up. So that's a change on the inside and the outside. So y equals x. If I'm going to the right, I know the default formula has a minus, and I would just be plugging in a positive 7 here. So it remains x minus 7 squared. And 4 units up is going to be a plus 4 on the outside. So the only other ones are the last 4. You've got to also look at making reflections happen and making vertical compressions or stretches happen. I didn't necessarily do all of those with you with the writing, but what you're doing is you're taking this A, H, and K, and based on the description of what's happening, you're going to decide whether or not to put a negative out there, to change the number out front, change the number inside, change the number outside. Some of these you might be a little confused about at first, but I do want you to try the last 4 on your own, 17, 18, 19, and 20. I did most of this lesson with you. In fact, I don't think that there was really any of them in the beginning that I asked you to do. So I just need you to try those last 4.